With ideally distributed data, as shown in the left panel, the ordinary least squares, or OLS, regression line effectively captures the positive relationship between innovation investment and GDP growth. It provides a robust representation of the overall trend in well-behaved datasets. However, the picture changes dramatically when we introduce just one single outlier, as seen on the right. This solitary data point, an extreme observation, pulls the entire OLS regression line downwards, completely reversing the perceived relationship from positive to negative. This stark visual demonstrates the immense fragility of OLS. A single data point is indeed enough to severely distort a standard economic model. The underlying reason for this sensitivity is that OLS minimizes squared errors, which gives outliers a disproportionate, quadratic influence, making them incredibly powerful in skewing the model's outcome. This flowchart outlines a critical decision-making process when working with linear regression models. We always begin by running a diagnostic check after fitting our initial OLS model. If the classical OLS assumptions are met, we can confidently report our OLS results. However, if assumptions are violated, we must identify the specific type of violation. If we detect heteroscedasticity, a common issue where the variance of the errors is not constant, we should use robust standard errors. This corrects our inference without changing our OLS coefficient estimates. But if the violation is due to outliers or data contamination, this is where robust regression, particularly estimation, becomes essential. Unlike simply deleting data points, robust regression dampens the influence of contaminated observations, allowing us to estimate the underlying relationship for the majority of our data without discarding valuable information. This methodological upgrade ensures more reliable and representative findings when extreme values are present. When choosing an estimator, we face a crucial trade-off between efficiency and resistance. Efficiency refers to the precision of our estimates, where OLS is 100% efficient under ideal conditions. However, the breakdown point measures an estimator's resistance, the minimum percentage of contaminated data it can handle before producing an arbitrarily bad result. As you can see, OLS has a breakdown point of 0%. Even one bad data point can completely distort its findings. estimation, an older robust method, offers good efficiency at 95%, but its breakdown point is still near 0% because it struggles with bad leverage points. This is where estimation shines. It provides a high breakdown point of 50%, meaning it can withstand contamination in up to half of the data, while still maintaining high and adjustable efficiency, typically between 70% and 95%. This makes estimation the modern standard for robust regression, offering a powerful balance of resistance and precision, much like choosing an off-road truck for rugged terrain over a Formula One car designed for a perfect track. Given this clear superiority, it's essential to use the right tools for implementation. The core idea behind robust regression is intuitive. It's about reweighting the data. Ordinary least squares, as shown in the top panel, gives every single data point an equal weight of 1. An outlier has the same vote as any other point, but because of its extreme position, its influence on the regression line is magnified, pulling the entire model off course. Robust methods, depicted in the bottom panel, operate differently. They iteratively identify points that deviate significantly from the overall pattern, those with large residuals, and reduce their weight, effectively pushing their influence towards 0. This means the outlier loses its vote, allowing the regression line to be determined by the bulk of the well-behaved data. Mathematically, this shifts our objective from minimizing the sum of squared residuals, which heavily penalizes large errors, to minimizing a function that is far less sensitive to these extreme values. Not all unusual data points are created equal. This slide breaks down the anatomy of different types of outliers and their distinct impacts on a regression model. A vertical outlier has an unusual y value, but its x value is within the typical range, primarily affecting the model's intercept. Then we have leverage points, which are observations with unusual x values. A good leverage point maintains the overall trend and, surprisingly, can even improve the precision of our slope estimate by extending the range of our predictor. However, the most problematic type is the bad leverage point. These points have both unusual x and y values, and crucially, they deviate significantly from the underlying trend. Bad leverage points are particularly dangerous because they can drastically tilt the slope of our regression line, leading to severely biased results. It's important to remember that standard M estimators, while helpful for vertical outliers, often fail to adequately address these dangerous bad leverage points. This is where more advanced methods like estimators become indispensable, as they are designed to robustly handle both types of issues. The interpretation of coefficients from OLS and robust regression is fundamentally different. An OLS coefficient estimates the mean change in y through a unit change in x. Because it relies on the mean, it is highly sensitive to every single data point, including measurement errors or extreme outliers. In contrast, a robust coefficient estimates the relationship for the bulk or majority of the data. It aims to represent the underlying, uncontaminated trend, effectively ignoring the noise from outlying observations. This difference leads to a powerful diagnostic insight. If your OLS and robust estimates differ significantly, it's a strong signal that your OLS result is likely being driven by a few extreme events or shocks, rather than reflecting a general economic law or consistent pattern. This comparison helps us understand the true stability of our observed relationships. When performing robust regression in Stata, it's important to differentiate between legacy and modern approaches. The legacy command, rreg, implements an M estimator. While it offers some robustness, it has a low breakdown point, meaning it's vulnerable to bad leverage points and significant structural shocks in your data. It's often best to avoid rreg if you suspect such issues. The modern, and highly recommended, approach is to use the user-written mmregress command. This is an estimator, which is considered the gold standard as it effectively handles bad leverage points and offers a high breakdown point. You'll typically need to install it first using ssc install mmregress. A critical tip for both legacy and modern robust estimators is to always declare your dummy variables explicitly using the dummies option. This prevents the algorithm from mistakenly treating large categorical shifts in your data as outliers that should be downweighted, ensuring more accurate results. When performing robust regression in Stata, particularly with the estimator, there are several key options to consider for fine-tuning your analysis. First, the FF-N option controls the efficiency of the Gaussian estimator. Setting the efficiency, often to 70%, provides a good balance between robustness against outliers and the precision of your estimates. While a higher efficiency, like 95%, makes the robust estimator behave more similarly to OLS, it can reduce its protective qualities against extreme values. Next, the GenWT-name option is vital for weight generation. It creates a new variable containing the specific weight from 0 to 1, assigned to each observation by the robust algorithm. This allows you to visually inspect and understand which data points were downweighted, providing crucial insights into the estimator's performance. Lastly, the cluster-varname option handles clustering of standard errors. This is essential for panel-style data or when observations within specific groups, like firms or regions, might be correlated. It ensures that your standard errors are correctly estimated, leading to valid statistical inference. For our case study, we'll analyze a dataset comprising 50 U.S. states plus Washington, D.C. Our objective is to model the crime rate using two key predictors, the poverty rate and the percentage of single-parent households. Looking at the summary statistics displayed, we can immediately identify some red flags. Notice the maximum crime rate of 2,922, which is significantly higher than the mean of 612.8. Similarly, the maximum values for poverty at 26.4 and single-parent households at 22.1 are also quite elevated compared to their respective means. These wide ranges and extreme maximums strongly suggest the presence of potential outliers within our dataset. This initial descriptive analysis is crucial, acting like a doctor checking vital signs before a diagnosis. It helps us get a feel for the data and identify any unusual observations that could heavily influence our subsequent modeling. With these potential outliers in mind, our first modeling step should be to formally diagnose their influence. To effectively address outliers, our first step is to diagnose their influence using a leverage versus residual squared plot. On this chart, the y-axis represents the normalized squared residual, which indicates how much a point deviates from the model's prediction. The x-axis shows leverage, reflecting how unusual a point's predictor values are. The most critical region is the top right quadrant, where observations exhibit both high leverage and large residuals. These are the bad leverage points that can severely distort our OLS regression. As we can clearly see, Washington, D.C. stands out in this dangerous quadrant. Its unique characteristics mean it's a structural outlier that will heavily pull and distort the OLS slope. Much like a single outlier in a security screening setting, it raises all the alarms. Identifying such points is crucial before proceeding with our robust analysis. Here we run the mmregress command in Stata. We regress crime on poverty and single. We set the efficiency to 70% using the F70 option. This provides a good balance between robustness and precision. We also use the dummy state option. Although in this simple model it's less critical, it's good practice to declare categorical identifiers. The results show that the coefficient for single-parent households is 175.9 and is highly statistically significant. The coefficient for poverty is 11.69, but it is not statistically significant at conventional levels, with a p-value of 0.139. Running this command is like calling in a specialist. We've done the initial diagnosis, the plot, and now we're using a specialized tool, mmregress, to perform the main procedure, carefully setting its parameters, F70, for the best outcome. These results are interesting, but their true meaning becomes clear only when we compare them to the standard OLS results. This is the aha moment. Now we arrive at the aha moment, the critical comparison between our standard OLS estimates and the robust estimates, after identifying and downweighting the outlier, Washington, D.C. For poverty, the OLS coefficient was small at 6.79 and not statistically significant. However, the robust estimate significantly increases to 11.69 and becomes borderline significant. This transformation clearly demonstrates that once the disproportionate influence of DC is removed, the true underlying positive relationship between poverty and crime for the other 50 states emerges, becoming both stronger and clearer. In contrast, the coefficient for single-parent households remains robustly positive and highly significant in both models, confirming its strong and consistent impact regardless of the outlier. The notable shift in both the intercept and the poverty coefficient between the two models serves as a strong indicator that our initial OLS model was indeed biased by the influential outlier. By applying the estimator and effectively removing DC's distorting influence, we gain a much clearer and more accurate understanding of the relationships for the majority of the U.S. states. This visualization, our fourth step, clearly illustrates the automatic reweighting process performed by the estimator. Each dot represents a state, and its vertical position indicates the final weight assigned to it, ranging from 0 to 1. A weight of 1 signifies full inclusion in the model, while a weight near 0 means the observation was effectively ignored due to its outlier characteristics. As you can see, the vast majority of states received a weight of 1, indicating they conform to the general structural logic of the data. However, the algorithm decisively identified Washington, D.C., and to a lesser extent, Mississippi, as outliers. These observations were assigned near 0 weights, significantly reducing their influence on our regression estimates. This transparency confirms that our robust model is indeed focusing on the underlying relationships within the bulk of the data, rather than being distorted by a few anomalous states. After running our robust model and interpreting its results, the final crucial step is to perform a series of validation and robustness checks. First, we conduct a visual inspection. We should always plot the fitted robust regression line over the scatter plot of our data. A properly fitted robust line will visibly pass through the bulk of the data, clearly demonstrating that it ignores the influential outlier. Second, an efficiency check is essential. Here, we compare the standard errors from our robust model to those from the OLS model. If the robust standard errors are significantly larger, it might suggest we've sacrificed too much precision. In our case study, they were comparable, indicating an acceptable trade-off. Finally, we perform a formal Hausman-style test. This test assesses whether the robust coefficients are statistically different from the OLS coefficients. If they are not, following Occam's razor, we might favor the simpler OLS model. However, if they are statistically different, as observed in our case study, it strongly justifies the use of the robust model, confirming its necessity. First, remember the reality of data. Outliers are not simply errors. They often contain valuable information about unique events or subgroups. The goal is not to delete them, but rather to downweight their influence so they do not distort the underlying general structure of your model. Second, it's crucial to utilize modern tools. Move beyond legacy commands like rreg in statistical software. Instead, use advanced high-breakdown estimators such as mmregress or rreg, which are specifically designed to handle the most problematic outliers, known as bad leverage points. Finally, always embrace comparative analysis. Present your ordinary least squares and robust regression results side by side. The true insight and the most interesting part of your story often lie in the differences between these two sets of results, as this reveals the sensitivity of your findings and the influence of extreme observations.